Welcome to another deep dive with us. We're going to be stepping into the world of statistical mechanics today.
Okay.
And, this is a topic which is very relevant to physics, but it also has these really deep philosophical questions kind of baked into it.
That's right. Yeah. I mean, when you think about it, statistical mechanics, or SM for short, it's all about trying to connect the microscopic world and the macroscopic world.
Right.
How do all these tiny little particles doing their own thing,
Yeah.
how does that lead to the big stuff that we see, like ice melting or gases, filling up a room?
Yeah. Or like, I was thinking about like, how do all the ants in an ant colony somehow work together?
That's a great analogy. Yeah, it's like
Yeah.
you've got all these individual little agents, and yet somehow they create this like organized structure.
Right. And so is that kind of the big goal here with statistical mechanics is to figure out how that happens?
Exactly.
Yeah.
Yeah, it's like trying to find the hidden rules that connect the micro to the macro.
Okay. And so where do we even begin with something like that? I mean, it seems like such a huge problem.
Well, one of the key concepts in SM is this idea of equilibrium.
Okay, equilibrium. I mean, I've heard that term before, obviously, in philosophy, but
All right.
how does it apply to physics?
So in SM, it's about the state that a system settles into after all the initial chaos has kind of died down.
So it's like if you shake up a snow globe
Yeah.
and then you let it settle, all the little particles will eventually find their...
Exactly. Yeah, they'll reach a state where things are relatively stable.
Yeah.
Not much is changing at the macroscopic level.
Okay, but how do we actually connect that idea of equilibrium to the world of particles, constantly bouncing around
Right.
and interacting?
So that's where SM gets really interesting. There are a few different approaches to tackling this question, each with its own philosophical implications.
Okay, so we've got multiple ways of looking at the same problem.
Exactly. Yeah, but before we get into those different approaches, it's helpful to clarify a key distinction between microstates and macrostates.
Okay, microstates and macrostates. Now, those sound familiar from like intro physics, but
Right.
maybe we should just refresh our memories,
Yeah.
for our listeners who might not be physicists.
Yeah, so a microstate, it's like a super detailed description of the system.
Right.
It tells you the exact position and momentum of every single particle.
So if we're thinking about our gas in a box example,
Yeah.
a microstate would specify the exact coordinates and speed of each gas molecule.
Precisely, yeah. Like if you could freeze time and take a snapshot of all those molecules, that would be a microstate.
Okay, that sounds pretty complicated. And what about macrostates then?
So a macrostate is more like a big picture view.
Okay.
It describes the system in terms of properties that we can actually measure, like temperature, pressure, or volume.
So instead of worrying about each individual molecule,
Yeah,
a macrostate just tells us the overall state of the gas, like it's 30 degrees Celsius and it's filling half the box.
exactly. Yeah. And the important thing here is that a single macrostate can actually correspond to many, many different microstates.
So it's like saying the library is organized.
Right.
There are lots of different ways you could arrange the books, but the overall description is still the same.
Perfect analogy. Yeah, and that's one of the key insights of SM.
Okay.
This idea that the macroscopic properties we observe are actually the result of countless different microscopic arrangements.
So it's all about how those microstates kind of average out to give us the macrostate.
Exactly. Yeah, and the different schools of thought in SM are all trying to figure out how exactly that connection works.
So we're talking about how the chaos at the micro level somehow leads to the order that we see.
That's a great way to put it, yeah. And one of the most influential approaches to this problem is called Boltzmannian statistical mechanics, or BSM,
Okay, BSM, named after Ludwig Boltzmann himself.
the one and only.
All right, so tell me, how does this BSM approach visualize this connection between microstates and macrostates?
Well, imagine we take the entire space of possible particle arrangements, all those microstates.
Yeah.
And we divide it up into different regions, each representing a different macrostate.
So it's like we're grouping together all the microstates that share the same macroscopic properties.
Exactly. Yeah, you might have a region for all the gas being on one side of the box and another region for the gas being evenly spread out.
Okay, so we're essentially creating a map of all the possible ways the system could be arranged.
That's a good way to think about it. And now here comes the key claim of BSM.
All right, I'm ready.
The equilibrium state of a system is the macrostate that has the largest number of corresponding microstates.
So the equilibrium state is the one that's the most probable statistically.
Exactly. Yeah. It's like saying that the most likely way to find a system is in the state that has the most ways to be arranged microscopically.
Okay, so it's all about playing the numbers game. The state with the most microstates wins
You got it. Yeah, it's like saying that a messy room is statistically more likely than a perfectly tidy room.
because there are just so many more ways for a room to be messy.
Precisely. Yeah, and that's the basic intuition behind BSM.
Okay, but doesn't that kind of imply a sort of determinism where systems are almost inevitably drawn to equilibrium?
You've hit on a key philosophical challenge to BSM known as the reversibility objection.
Reversibility. Hmm. So are we saying that systems can't actually move away from equilibrium?
Well, the laws of physics governing individual particles are often time reversible. So theoretically, if we could play a microscopic film of a system evolving in reverse, it would still obey the laws of physics.
So if we could rewind the film of gas spreading out to fill a box, should we see it bunch back up into a corner just as easily?
Yeah, that's the crux of the objection. It seems to contradict this idea of an irreversible approach to equilibrium.
So how does BSM address this puzzle?
Well, it has a few tricks up its sleeve.
Okay, this is where it gets interesting. I'm eager to hear those tricks.
One way BSM tackles this is through the lens of ergodic theory.
Ergodic theory. Okay, now that
A
sounds,
bit intimidating.
yeah, a bit
It
intimidating.
might sound complicated, but the idea is pretty elegant. It's about looking at the long-term behavior of systems.
Okay, so we're thinking about vast stretches of time.
Exactly, yeah. And ergodic theory basically says that an ergodic system over those long periods will visit each of its possible microstates for a duration proportional to the size of that state's region in the space of possibilities.
So since the equilibrium state has the biggest region because it has the most microstates, the system will spend most of its time there.
Exactly, yeah. And from there, you can develop a probabilistic interpretation. The longer a system spends in a state, the higher the probability of finding it in that state.
So it's not that systems can't move away from equilibrium. It's just that they're overwhelmingly likely to be found in equilibrium.
That's a great way to put it, yeah.
Okay, but if it's all about probabilities, how does BSM handle the recurrence objection? Doesn't Poincaré's recurrence theorem say that even in a closed system, particle arrangements will eventually repeat?
You're right. Yeah, the recurrence objection is a classic challenge to any theory that tries to explain the irreversible approach to equilibrium.
So wouldn't that mean that even a gas that's spread out should eventually unequilibrate and bunch back up?
Well, BSM acknowledges that recurrence is theoretically possible, but the timescales involved are astronomically huge, often exceeding the age of the universe itself.
So it's possible, but incredibly unlikely.
Exactly. Yeah, like saying if you flip a coin for long enough, you'll eventually get a million heads in a row.
But I wouldn't bet on it happening anytime soon.
Right, exactly.
Okay, so BSM uses these vast timescales and probabilistic arguments to address these philosophical objections.
Yeah,
But are there any responses that dig a bit deeper into why equilibrium is so special?
absolutely there are. And one fascinating approach is championed by physicist David Albert, and it connects the microworld to the grand scale of the universe's origin.
Okay, that sounds intriguing. How do we get from particles in a box to the Big Bang?
It all hinges on a concept called the past hypothesis.
The past hypothesis.
Right, I'm listening.
This hypothesis suggests that to understand why entropy tends to increase, we need to consider the very starting point of the universe, the Big Bang.
So we're going all the way back to the beginning of time to explain why systems reach equilibrium. In a way, yes. The past hypothesis posits that the universe began in an incredibly low entropy state, highly ordered, and from that initial point, as the universe has evolved, entropy has been steadily increasing.
So the universe started out super organized and it's been getting messier ever since.
That's a very simplified way of putting it, but you got the idea.
Okay, but isn't that just pushing the problem back a step? Now we have to explain why the universe started in such a low entropy state.
That's a great point, and it's a major point of debate. Some argue that the past hypothesis is just a fundamental law of nature, something we have to accept as a starting point. Others think it might point to a deeper explanation, maybe from quantum gravity or cosmology.
So we've gone from particles in a box to the origin of the universe in just a few steps.
It's quite a journey.
It is. And this past hypothesis really adds a whole other layer of intrigue to this discussion. But you mentioned earlier that there are other approaches to SM. We've talked a lot about BSM. What's next on the agenda?
Well, next up, we're going to dive into Gibbsian statistical mechanics, or GSM.
GSM. All right, so another approach to the same problem.
Exactly. And GSM takes a slightly different route, relying on the concept of ensembles.
Ensembles. Okay, now that sounds like we're getting even more abstract.
In a way, yes. Instead of focusing on a single system, GSM looks at an imaginary collection of infinitely many copies of the system, each in a different microstate.
So it's like we're creating a library of all the possible ways our gas could be arranged.
Precisely. Yeah. And each ensemble, this collection of systems, is characterized by a probability distribution, which tells you how many systems are in each particular microstate.
Okay, so instead of tracking the actual trajectory of a single system, we're creating a statistical snapshot of all possible configurations.
Exactly.
But how does GSM actually explain the approach to equilibrium? If this probability distribution is stationary, doesn't that mean nothing really changes?
That's the key challenge for GSM, and it relates to a concept we've touched upon before, entropy.
Okay, entropy, right back to
Yeah.
entropy.
Just like in BSM, entropy in GSM is a measure of disorder or uncertainty, but in GSM, it's a property of the whole ensemble, not of an individual system.
So we're not talking about the entropy of one specific gas in a box. We're talking about the entropy of this entire imaginary collection of gases.
Precisely. Yeah, and here's the kicker. The math of GSM implies that the entropy of an ensemble, also known as the Gibbs entropy, never changes. It's a constant of motion.
Wait, but if entropy is constant, how can we describe a system approaching equilibrium, which is supposedly all about entropy increasing?
It's a big puzzle. How can a theory with a constant entropy account for the seemingly irreversible tendency of systems to move towards equilibrium?
Yeah, that doesn't seem to make sense.
It's a real head-scratcher, and GSM has spurred a variety of attempts to reconcile this apparent contradiction.
Okay, so there are ways to address this problem.
There are. And these attempts, as we'll see, touch upon some deep philosophical questions about the nature of knowledge probability and even the role of the observer.
This is getting really interesting. All right, so let's dive into those attempts to unravel this entropy puzzle in part 2 of our deep dive.
All right, so we're back to this puzzle of how GSM can explain equilibrium even though ensemble entropy is constant.
Right. Seems like a bit of a contradiction.
It is, but GSM has some clever solutions up its sleeve. One approach involves a concept we mentioned earlier, coarse graining.
Ah, coarse graining. Like putting on blurry glasses and seeing the world in lower resolution.
That's a great way to think about it, yeah. In GSM, coarse graining means you're essentially blurring your vision of the microscopic details. Instead of keeping track of every single microstate, you're averaging over small regions of state space.
So instead of worrying about the exact arrangement of every book in the library, we're just concerned with how many books are on each shelf.
Exactly. And when you calculate entropy using this coarse-grained distribution, something interesting happens.
What's that?
The coarse-grained Gibbs entropy can actually increase over time.
Really? So by blurring our vision, we've somehow allowed entropy to change.
It's kind of counterintuitive, but that's the beauty of it. This coarse-grained entropy keeps increasing until it reaches a maximum, which corresponds to a state of quasi-equilibrium.
Quasi-equilibrium. So it's like a blurred version of the true equilibrium state where things might not be perfectly uniform at the microscopic level, but it looks pretty even from our macroscopic perspective.
Precisely. It's like looking at a pointless painting. Up close, you see all the individual dots, but from afar, they blend together to create a smooth image.
I love that analogy.
Yeah.
So coarse graining allows entropy to increase, and the system approaches this blurred equilibrium.
Yeah.
But does this work for all systems?
That's where things get a bit tricky. The success of coarse graining depends on the system being what we call mixing.
Mixing, like stirring ingredients in a bowl.
Exactly. A mixing system is one where any initial subset of microstates will eventually spread out evenly throughout the entire state space over long periods of time. But this mixing property is a pretty strong requirement.
So not all systems will nicely reach this quasi-equilibrium through coarse graining.
Unfortunately not. And even for systems that are mixing, this perfect spreading out only happens in the infinite time limit.
Yeah.
Real systems reach equilibrium much faster.
So coarse graining gives us a way to understand how entropy can increase, but it's not a universal solution. Are there other explanations within GSM that don't rely on this blurring?
There are. And another interesting approach challenges this assumption of perfect isolation that we often use in these thought experiments.
Right, the classic gas in a perfectly insulated box.
Exactly. In reality, no system is truly isolated. There are always tiny interactions with the environment, little nudges and bumps that can influence the system.
So our neat little picture of a closed system breaks down when we consider these messy real-world interactions.
Precisely, and that's where the interventionist approach comes in. This view suggests that these small, random interactions with the environment are actually what drive systems towards equilibrium.
So it's not just the system itself. It's also these external kicks from the environment that can increase entropy and push the system toward equilibrium.
Exactly. Like if you gently shake a container of sand, those tiny shakes, even if random, will cause the sand to settle into a more uniform, higher entropy state.
Makes sense.
Mm.
But doesn't this just shift the problem to a larger system? Now we have to explain why the environment is causing these nudges.
That's a valid criticism. It's like an infinite regress. If the environment is pushing the system towards equilibrium, what's pushing the environment?
Dominoes all the way down.
Exactly. Proponents of interventionism often argue that the laws of physics might have limited domains of applicability. It's like saying the rules of chess apply to the chessboard, but not necessarily to the table it's on.
So the laws governing our system and its immediate environment might not apply to the entire universe.
That's one way to think about it, but of course this raises its own set of questions about the nature of laws and the limits of scientific explanation.
It seems like every time we try to answer one question in statistical mechanics, we just end up with more questions.
That's the beauty of it. It keeps us on our toes. But we did mention one more attempt to explain equilibrium within GSM. Do you remember?
Yes, the epistemic account. That's the one where we start thinking about knowledge in the observer.
Exactly. This is arguably the most philosophically radical approach. It basically says that statistical mechanics is about our knowledge of a system, not the system itself.
Okay, so we're shifting from the objective world of particles to the subjective realm of the observer.
In a way, yes. The key insight here is that Gibbs entropy has the same mathematical form as the Shannon entropy in information theory.
And Shannon entropy is all about information.
Right, precisely. It measures our lack of information about a system. So the more entropy a system has, the less we know about its exact microstate.
So the epistemic account says that the probability distributions in GSM actually represent our state of knowledge about the system, not some objective property.
Exactly. It's like the ensemble isn't a collection of real systems, but rather a representation of all the possible states our real system could be in, given what we currently know.
So equilibrium in this view simply means that we have the least amount of information about the system.
Exactly. And the approach to equilibrium is driven by us gaining more information about the system through measurements or observations.
So the act of observing is bringing order to the chaos.
It's a mind-bending idea, but it raises some really interesting philosophical questions. If SM is all about our knowledge, what does that say about the objective reality of things like the freezing of water? Are those just constructs of our minds?
Wow, it seems like every attempt to define equilibrium and entropy leads to even deeper philosophical questions.
That's what makes statistical mechanics so fascinating. It's a field that constantly challenges us to think beyond the equations and grapple with some of the biggest questions about the world we live in.
Well said. So for our listeners who have been on this deep dive with us, what are some key takeaways from our exploration of this mind-boggling field?
Well, we've seen that statistical mechanics isn't just a dry technical subject. It's a field that grapples with profound questions about time, causality, probability, and the relationship between the observer and the observed. We've encountered different approaches, each with its own strengths, weaknesses, and philosophical baggage.
We've explored the concept of entropy and its relationship to equilibrium, and even considered the possibility that the universe's starting conditions might influence everyday phenomena. And along the way, we've been forced to confront the limits of our current understanding.
Indeed. And perhaps the most important takeaway is that statistical mechanics, like all great scientific endeavors, isn't just about finding answers, it's about asking the right questions. And those questions, as we've seen, often lead us into the realm of philosophy, where the boundaries between physics, metaphysics, and epistemology start to blur.
Absolutely.
Yeah.
So to our listeners, as you go about your day, I encourage you to see the world through the lens of statistical mechanics. Notice the patterns of order and disorder, the tendency towards equilibrium, and the interactions between systems and their environments, and never stop questioning the assumptions that underpin our understanding of the universe.
And who knows, you might just stumble upon the next big breakthrough.
That's all for this deep dive. Thanks for joining us, and until next time, keep exploring, keep questioning, and keep seeking knowledge.
All right, so remember that puzzle we left off with? How can GSM explain equilibrium when ensemble entropy is always constant?
Right. It's like a system moving towards more disorder while the measure of disorder stays the same.
Exactly. A bit of a head-scratcher. But GSM has a few more tricks up its sleeve. One approach involves something called coarse graining. Remember that?
Yeah, like putting on blurry glasses and seeing the world in lower resolution.
Exactly. That's a great way to think about it. So in GSM, coarse graining means you're basically ignoring some of the fine-grained details of the microstates. You're averaging over little chunks of the state space instead of looking at every single microstate individually.
Okay, so it's like saying instead of worrying about the precise position of each book in the library, we just care about how many books are on each shelf.
Precisely.
Oh.
And when you calculate entropy using this blurred, coarse-grained distribution, something interesting happens.
What happens?
The coarse-grained Gibbs entropy can actually increase over time.
Wait, really? So by blurring our vision, we've somehow allowed entropy to change?
It seems counterintuitive, but yeah, that's the idea. This coarse-grained entropy will keep increasing until it reaches a maximum, and that corresponds to a state of quasi-equilibrium.
Quasi-equilibrium. So it's like a kind of blurred version of true equilibrium.
Exactly. Things might not be perfectly uniform at the microscopic level, but macroscopically it looks like equilibrium.
Okay, I'm starting to see how this might work. But does this coarse graining approach work for all systems?
Well, that's where things get a bit more complicated. For coarse graining to work, the system needs to have a property called mixing.
Mixing, like stirring ingredients in a bowl.
Exactly. A mixing system is one where any initial set of microstates will eventually spread out evenly throughout the entire state space over long periods of time. Think of it like those ingredients getting thoroughly mixed in your bowl.
Okay, but doesn't that take a really long time?
Yeah, that's the catch. This perfect mixing only happens in the infinite time limit.
Ah, so not very practical for us finite beings.
Right. Real systems tend to reach equilibrium much faster. So while coarse graining is a neat idea, it's not a universal solution.
So are there any other explanations within GSM that don't rely on this blurring technique?
There are. And one intriguing approach challenges a very common assumption in these thought experiments, the assumption that our systems are perfectly isolated.
Yeah, the classic gas in a box scenario.
Exactly. In reality, there's no such thing as a perfectly isolated system. There are always tiny interactions with the environment, little nudges and bumps from the outside world.
So our neat little picture breaks down when we start thinking about the real world.
It does.
Yeah.
And that's where the interventionist approach comes in. This view suggests that those little interactions with the environment are actually what drive systems toward equilibrium.
So it's not just the internal dynamics of the system, but also these external nudges that increase entropy.
Precisely. Think about it like gently shaking a container of sand. Even if those shakes are random, they'll still cause the sand to settle into a more uniform, higher entropy state.
Okay, that makes sense.
Yeah.
But doesn't this just shift the problem? Doesn't it mean we have to explain where those nudges from the environment are coming from?
But that's a valid point. It leads to a kind of infinite regress. If the environment is pushing the system toward equilibrium, then what's pushing the environment?
Right. It's like explaining one domino falling by saying another domino pushed it.
Exactly. So proponents of this interventionist view often suggest that maybe the laws of physics have limited domains of applicability.
So the laws governing our system don't necessarily apply to the entire universe.
That's one way to think about it. But it definitely raises more questions about the nature of laws and the limits of science.
It seems like statistical mechanics is a field that generates more questions than answers.
In a way, yeah. But that's what makes it so interesting. It forces us to confront the limits of our understanding. But before we wrap up, there was one more attempt to explain equilibrium within GSM that we haven't talked about yet.
Oh, right, the epistemic account. The one that brings in the observer and their knowledge.
Exactly. This one is perhaps the most philosophically radical of them all. It basically reinterprets statistical mechanics as being about our knowledge of a system rather than about the system itself.
Okay, so it's a shift from the objective to the subjective.
In a way, yes. The key insight here is that the Gibbs entropy, the measure of disorder we've been talking about, actually has the same mathematical form as something called the Shannon entropy.
And Shannon entropy is all about information, right?
Exactly. It quantifies our lack of information about a system. So the more entropy a system has, the less we know about its specific microstate.
So in this epistemic account, those probability distributions we use in GSM are actually representing our knowledge about the system.
Precisely. It's like saying the ensemble isn't a collection of real systems, but rather a representation of all the possible states our real system could be in, given what we currently know.
Okay, so equilibrium in this view means we have the least amount of information about the system.
Exactly. And the approach to equilibrium is driven by us gaining new information, maybe through measurements or observations.
So the act of observing itself is what's bringing order to the chaos.
It's a pretty mind-bending idea, but of course it raises its own philosophical questions. If SM is all about knowledge, then what does that say about the objective reality of things like the freezing of water? Is it all just a construct of our minds?
That's a deep question.
Yeah.
And it seems like every time we try to define equilibrium and entropy, we end up with even more philosophical questions.
That's the beauty of statistical mechanics. It's a field that constantly pushes us to think deeper about the nature of reality knowledge and the limits of scientific explanation.
Well said. So for our listeners who've been on this deep dive with us, what are some key takeaways from our exploration of this fascinating and often mind-boggling field?
I think one key takeaway is that statistical mechanics isn't just a dry technical subject. It's a field that grapples with some of the most fundamental questions about the universe. We've seen how it connects the microscopic world to the macroscopic world, how it deals with the concepts of entropy and equilibrium, and how it even touches on the very origins of the universe.
We've also seen that there are multiple approaches to SM, each with its own strengths, weaknesses, and philosophical implications. And along the way, we've encountered some really deep questions about the nature of time, causality, probability, and the role of the observer.
And perhaps the most important takeaway is that statistical mechanics, like all great scientific endeavors, is not just about finding answers, but about asking the right questions. And those questions, as we've seen, often lead us into the realm of philosophy, where the boundaries between physics, metaphysics, and epistemology become blurred.
Absolutely. So to our listeners out there, I encourage you to keep thinking about these ideas. Keep noticing the patterns of order and disorder, the tendency towards equilibrium, and the subtle ways that systems interact with their environments. And never stop questioning the assumptions that underlie our understanding of the world.
Who knows, you might just stumble upon the next big breakthrough in this fascinating field.
That's all for this deep dive. Thanks for joining us, and until next time, keep exploring, keep questioning, and keep seeking knowledge.